Okay, maybe I can now introduce Loh Huanqian, okay, the next speaker. Okay, so Huanqian is a President's Assistant Professor at the Department of Physics of National University of Singapore, a colleague of mine. She's also a principal investigator at the Center for Quantum Technologies, and she group research is dealing with the control of optical tweezers arrays of ultra-cold atoms, like reconfigurable quantum building blocks. She did her PhD at GILA, University of Colorado, and then her postdoc at CQT, and finally she got hired at NUS. Okay, recent awards include the World Economic Forum Young Scientist Award and the L'Oréal UNESCO for Women in Science International Rising Talent Award. So Huanqian will talk to us about single atom control with optical tweezers arrays.
Thank you very much for the introduction. And also thank you to the organizers for the very kind invitation to talk at this conference. I also don't work directly in the field of atomtronics, so I was very pleasantly surprised by the invitation. But I found this to be a very illuminating conference, learning about soliton waves, expanding universes, and even just now about variational optimization as applied to trapped ions. So today I'm going to discuss actually a slightly different platform that was mentioned at the end of Peter Zoller's talk just now, which is optical tweezer arrays. So these are some very recent results that came out of my group. They are published in an archive paper on basically the methods that we have recently come up with to increase the scalability of atom arrays using magic wavelengths. So you see here actually just a cartoon of an array of tweezers, each of them having a singly trapped atom. And here actually we are relying on operating the tweezer at a wavelength that cancels exactly the differential light shift between the ground and the excited state. Okay. So the different AMO platforms that have now become very popular for quantum simulation and quantum computation are listed below. We just heard a whole talk about trapped ions, a very beautiful talk. And also alongside with superconducting qubits, which are also a popular platform in atomtronics. These two platforms have really garnered a lot of industry attention in the last several years. And that's really because they are able to achieve individual qubit control in a very scalable manner. And in terms of academic research, also there's been a lot of research on putting ultra-cold atoms in optical lattices. So here you see a picture of the quantum gas microscope, where you're able to have single-site addressability and also single-site detection. So I will not talk very much about any of these different platforms, and also that includes photons and more solid-state-based platforms like color centers in diamond and dopants in silicon. But rather, I will introduce tweezer arrays, which, as I mentioned before, they are really arrays of tightly focused beams where you have single atoms trapped or even single molecules trapped. And the key advantages are really that there are a lot of things that you can control with these tweezer arrays. You control not only the internal states, but also the motional quantum states by cooling them down, for instance, to the ground motional quantum state using Raman sideband cooling. It has also been demonstrated that with these tweezer arrays, you can generate them in first 1 dimension, 2 dimensions, and also 3 dimensions. You can actually control the geometry very well by arbitrarily rearranging these atoms in real time. And you can also control the doping. And finally, to make all of these atoms and molecules interesting for the various applications, they need to have some form of long-range anisotropic interactions. So these are usually induced by exciting the atoms to highly excited Rydberg states or by working with ground state dipolar molecules. So with these tweezer arrays, they've really exploded in the last few years since they were first demonstrated in 2001. And some of the popular applications include quantum simulations, where here you can explore not only different phases of quantum magnetism, but also many-body dynamics and topological physics. They are also used for quantum computation. So basically by using the dipolar interactions, you can have phase gates. It's been demonstrated, the Toffoli gate, for instance, has been demonstrated with these Rydberg arrays. You can also use them for metrology, as is now pursued by trapping alkaline earth atoms inside these tweezers, as demonstrated by groups at Caltech Gila, for instance, where they have gotten a half-minute clock. And finally, tweezer arrays are actually quite useful for studying single molecule physics and chemistry. There are two ways that you can do this. You can either trap arrays of molecules that are already preformed, just like calcium fluoride, from a buffer gas cooled cloud of molecules that's then trapped in a magneto-optical trap. Or you can actually tweezer trap individual atoms and then assemble them together to form ground state dipolar molecules, as I will discuss towards the very end of this talk. So one of the key reasons why the tweezer arrays have really exploded in the last few years is a key enabling technique that was demonstrated in 2016 or so, which is the ability to rearrange these atoms in real time in a manner that gives you defect-free atom arrays. And this defect-free part is actually very important because it turns out that when you have an array of, say, 100 tweezers over here, you're only stochastically going to load maybe about 50, maybe 60% of these tweezers, which means that you have about 50 to 60 traps that are randomly filled, and that's not very friendly for, say, quantum simulation, mapping onto a particular Hamiltonian, or quantum computation, where you really want to control the exact kind of array that you're working with. So the way this is done, there are several ways, but I'm going to highlight some of them here, is that you can use, for instance, an acousto-optic deflector to generate the tweezer arrays. And then in these 100 traps, you maybe trap about 50 atoms and 50 of them. You image in real time how many of these traps are filled using atom fluorescence, drop the traps that are empty, and then shuffle the rest of the traps together such that you get this defect-free array. This can be done on the scale of tens of milliseconds, so essentially real time, by using feedback from the EM-CCD camera back into this acousto-optic deflector. And what this acousto-optic deflector does is that it takes in a bunch of radio frequency tones and then converts those into different beam deflections, which are then imprinted as tweezers. So in other words, this method is quite nice and scalable, because if you want to align 100 different tweezers, it doesn't mean that you have to align 100 laser beams separately. It just means that you need to send in a laser beam that is about 100 times more powerful in order to generate the 100 tweezers. So it's really combining the individual qubit control with scalability in this case. So this was demonstrated for both 1 dimensions and also 2 dimensions in 2016. Since then, in the Broes group, they've taken it even to 3 dimensions, creating some very nice geometries over here. And besides acousto-optic deflectors, you can also perform the same thing with spatial light modulators and also a record rearrangement here in the Berkel group using microlens arrays. So going forward, we know that more tweezers are good. It means you have more qubits that are under control. But let's discuss some of the limits to scalability over here. So one of the things that could limit your scalability would be tweezer laser power. So how much power do you need? Well, let's say if you want to generate 1 tweezer trap that's about 1 millikelvin deep, you would require about 1 to 5 milliwatts of power in trap waves of 1 micron. Okay, so that's probably quite manageable, because if you can get lasers of about 1 to 10 watts, so you can easily get 10 to the 3 traps, 10 to the 2 to 10 to the 3 traps that way. You also want to make sure that you have efficient loading and detection of atoms. This could limit your scalability. If you can load 50%, okay, that means that out of 100 traps, 50 of them are filled. If you can load 90%, it means that out of 100 traps, 90% of them are 90 are filled. So that actually really goes a long way when you're trying to minimize the number of rearrangements that you do, so that you can get high fidelity rearrangement at the end. The other things that could limit your scalability would be, for instance, the radio frequency bandwidth of this acousto-optic deflector. So each acousto-optic deflector comes with several tens of megahertz of bandwidth. And again, the way this works is that it maps the radio frequency onto the trap separation, and it also maps the RF amplitude onto the trap intensity. So if you have some limited bandwidth, that means that there's only so many traps that you can generate. But you could argue, okay, I'm going to then just space the traps more closely together. But then you now run into the last limit, which is that if you space them too closely together, such that the RF frequency hits the parametric resonance of a trap frequency, then you would also start to heat the atoms out of the trap. So these two combined also give you a certain limit. But then in the Lukin group, as they've demonstrated, you can get something like 100 traps out of 1 dimension. So actually, if you concatenate this in 2 dimensions, you can already get 10 to the 4, which is actually a pretty reasonably large number. So most of the time in the tweezer array community, in terms of scalability limits, it's really got to do with the first 2 constraints, efficient loading detection, state preparation of the atoms. And this is actually what we want to tackle in this talk. So to efficiently load and detect the atoms, I just want to explain briefly that these single atoms that are loaded in the tweezer, they are loaded directly from a magneto-optical trap or molasses. There's no extensive evaporative cooling that goes on. So they're loaded from the molasses, which means that as they are loaded into the trap, the atoms actually experience this closed cycling transition where it spends some amount of time in the excited state, something like 25% of the time as well. So the atoms are in the ground in the excited state. And it would help a lot, actually, if you could have a tweezer wavelength that doesn't see very much of a differential light shift between the ground and excited states. So in other words, this tweezer wavelength, it being magic to the D2 closed cycling transition, actually helps you a lot with the efficient loading and detection. And this was first exploited by the Kimball group in 2003, where they use the D2 magic wavelength in cesium to detect single atoms in their cavity. And in fact, this idea of using magic wavelengths is not particular to the alkali atoms. They are also one of the reasons why the alkaline earth are very popular. They tend to have magic wavelengths, and these magic wavelengths are in fact relatively short. And that's also useful for their operation as optical clocks. But on the other hand, I want to highlight that among the different alkali atoms, cesium is actually the only atom that has a D2 that has a magic wavelength that has a wavelength that is magic to the D2 closed cycling transition, and the rest actually do not have that. So that's a bit of a pity. But how much of a deal breaker would it be if you do not have a magic wavelength? Well, let's examine this. So here you see a plot of the ratio of polarizability of the excited state relative to the ground state as a function of the tweezer wavelength. And you see over here that when you're on the magic transition, then at 930 magic wavelength at 935 nanometers, this beta parameter that's equals to 1, which means that the ground and the excited state have exactly the same trap slope, basically. So that's for cesium, but for rubidium, you see that this doesn't exist. But how bad is it really? Well, many people still work with rubidium tweezers, and that's because it's not such a bad effect in that case when you're operating at a typical tweezer trap wavelength of less than 50 nanometers away from the D1 wavelength. You're not getting, you have a very, very slightly anti-trapping excited state, but that's about it. And it's still okay compared to, say, the photon recoil energy that is gained from rubidium. Now, on the other hand, for some of the lighter atoms like sodium, even potassium, this actually becomes quite a problem. So in sodium, the D1 wavelength that's at 589 nanometers. 700 nanometers over here is significant because that's where the TISEF range begins. And over there already, the excited state, the D2 excited state is already about 1.2 times anti-trapping compared to the ground state. And this is a big deal when you're trying to load single atoms into the tweezers directly from a cloud that is cooled using the D2 closed cycling transition. And in fact, the group that tried this, the Ni group at Harvard, they were not able to load single atoms until they developed this technique of the AC tweezers, where basically you modulate the tweezer and the cooling light such that they are not on at the same time, so they're modulated out of phase, but at a frequency that is fast compared to the trap frequency. So you really want to avoid having any overlap between the cooling light and the tweezer light. So in this case, once the tweezer is on, you do not have the atom in the excited state. And to minimize this overlap, in fact, the tweezer duty cycle is not even 50%, it's usually about 30% or so to optimize the loading. So this AC tweezer technique turned out to be necessary to load and image the lighter atoms like sodium and potassium to prevent atom loss from the anti-trapping excited states. And in fact, in rubidium, it has also been used, for instance, by the RIGO group to image single atoms without problematic light shifts. So the AC tweezers presents a nice solution to the lack of the D2 magic wavelengths, but there are some issues with scalability. So firstly, in order to create a given trap depth, you require more tweezer power. In fact, it's about 1 over the duty cycle, so roughly 3 times more tweezer power. And secondly, when you use AC tweezers on the D2 line, you actually tend to require deeper traps. So our solution to this approach is to actually forget about the D2, we go straight to the D1. And we find that on the D1 line, so here's an example for sodium, the polarizability of the different states, we actually do have magic wavelengths. So this was first calculated by Aurora, Safronova, and Clark in 2007. So here you see an example where you've got magic wavelengths over here and also here around 660 nanometers. And in fact, very nicely, these D1 magic wavelengths are actually predicted to exist for all the alkali atoms, where you have positive and also relatively large polarizabilities. So these would be actually quite friendly for tweezer trapping. But these D1 magic wavelengths have not been observed or exploited before. So just to highlight a few more advantages of the D1 line, they have very well-spaced energy levels. And also there's no tensor polarizability component because it's just a J1/2 states for both the ground and excited state. So this is nice because it doesn't really complicate matters very much when you put them in a linearly polarized tweezer trap. And these D1 lines have been used for very nice gray molasses cooling, where the temperatures can be a factor of a few to 10 times colder than what you would actually get from the D2 polarization gradient cooled molasses. It has also been demonstrated that this D1 line can be used for lambda enhanced imaging. For loading, because the D1 gray molasses cooling requires a blue detuned light, there's actually a very nice mechanism that allows you to have enhanced loading. So taking a step back, when people usually load directly from red detuned molasses, in that case, what you're doing is that if you have 2 atoms that's present in the trap, they will be driven towards an attractive molecular state. And the kinetic energy that they gain in this attractive molecular potential will essentially actually kick the atoms out of the trap because it's too high of a kinetic energy. So this means that on average, you have either 0 or 1 atoms that are being detected. So it's kind of an odd or even parity detection. But on the other hand, when you're using lambda gray molasses light on the D1 line, that's blue detuned. So when it's blue detuned, you can now drive it actually to a repulsive molecular potential. And by doing so, you can actually tune the collision energy such that you're only left with just 1 atom in the trap at the end of this loading process. This was actually demonstrated first by the Anderson group in 2010 for relatively deep trap, 3 millikelvin. And then just 2 years ago, it was then demonstrated to work quite well even in very shallow trap depths of a few hundred microkelvin by the RIGO group. So combining all these together and really with the insight that you can make use of D1 magic wavelengths, we demonstrate over here actually an all DC approach now that you can use for loading and imaging single sodium atoms. And this together with the enhanced loading and the lower trap depths needed gives us a demonstrated order of magnitude increase in the scalability from the reduction in the trap power. Okay, so the way we perform these experiments is that we first load a magneto-optical trap with the D2 light, perform polarization gradient cooling, and then we switch to D1 light, and that's also when we turn on the tweezers. So in D1 light, we first perform some lambda gray molasses cooling just to further cool the atoms down. Then we carry out about 100 milliseconds of this enhanced loading by changing the detuning a little bit to tune the collision energy between 2 atoms more precisely. And then finally, we carry out our D1 imaging in DC. And this is the histogram that we typically get, a histogram of the photons that are scattered. So you see 2 peaks over here. And in fact, I want to add that what the DC-D1 imaging does is that it does not modify the trap population at the end of the loading process. So that means that if your loading process is actually not complete, you could potentially be left with multiple atoms, still like 2 atoms in the trap, and that would show up as multiple peaks in your photon scattered histogram. So to check that we are indeed loading a single atom, we actually change to, as a sanity check, AC-D2 imaging. Here again, we are rate detuned. And because it's rate detuned by the collisional blockade mechanism that I explained just now, we should be left with at most 1 atom in the trap. And with that, the histogram that we get is actually very similar to what we get from the DC-D1 imaging. So this gives us confidence that actually our loading process is complete, and we can actually rely on this sequence to be able to load single atoms into our traps. So with this, the first thing we do is to actually experimentally confirm where the D1 magic wavelength lies by basically measuring the differential light shift between the excited state and the ground state. So to do so, we use a probe light tuned to the D1 resonance to try to heat the atom out of the trap. And because we are working with the D1 line, we have to be very careful to avoid dark states. So this means avoiding hyperfine dark states, which we do by breaking the Raman detuning, by choosing some non-zero Raman detuning. And we also break the degeneracy between different Zeeman states simply by applying a magnetic field. And when we do so, okay, thanks. When we do so, we find that as we tune this principal detuning, we are able to find a resonance position when we're able to deplete the atom out of the trap. And we can do this as a function, and we can measure this resonance frequency position as a function of the different trap depths. And the gradient of this basically is sensitive to the differential light shift from the tweezer. The V and H that you see over here refers to the tweezer polarization. So again, because we're dealing with the D1 line, there's no tensor polarizability, only scalar and vector polarizability. In principle, if you use linearly polarized light, the vector polarizability should be 0. But then, because we're worried about some residual polarizability components from propagating through the glass and so on, we actually take 2 linear polarizations that are orthogonal to each other, vertical and horizontal, and then we take the gradients and we average those, such that what we're measuring is hopefully just the scalar polarizability component. So this is done for one particular tweezer wavelength, which we then vary for multiple tweezer wavelengths over here in the vicinity of where the magic wavelength is predicted to lie. So the black dots refer to the data with the error bars, and the red is actually a no-free parameter curve that is from Aurora, Safronova, and Clark. And we see actually relatively good agreement. The gray band over here is where the magic wavelength is predicted to lie, where the width of the band refers to the width that was given by theory in 2007. Okay, so this gives us some confidence that we are pretty much operating at the magic wavelength. And then the next thing we want to find out is the effect of this tweezer wavelength on the loading and imaging process. So for this, we want to decouple the two. First, we want to find out the effect of the magic wavelength on loading. So for that, we perform the usual sequence, but instead of doing DC-D1 imaging, we just use AC-D2 imaging such that it doesn't care about which tweezer wavelength we are at. So over this range that we are going to probe, we find that actually the ground state is not changing very much by just a few %, but the trap depth of the excited P1/2 state is actually changing quite a bit from being deeper on the at shorter wavelengths to being quite a bit shallower and even a little bit anti-trapping at higher wavelengths. And what we find is that actually, as long as we're able to compensate for the change in the differential stark shift at the trap center, we are still able to load with actually relatively high probability over here. So this tells us that the ability to compensate for this change tells us that the loading cools the atom actually really just to the trap center. And so this is actually working quite well for us. And also want to highlight that these probabilities that we detect are enhanced compared to the regime that you would expect for the collisional blockade. And this agrees with the kinds of numbers that were gotten previously in the other groups. So we haven't seen very much of an effect of the tweezer wavelength on the loading, just because we can compensate for it. But for the imaging, that's actually a different story. So now we switch to DC-D1 imaging. We use the same loading parameters that were optimized from before. But we find that actually, as we change the tweezer wavelength and we now re-optimize the D1 imaging parameters, we're not really able to compensate and always maintain our high loading probability. And this is because the atom is actually heating up during the imaging, and therefore this gives rise to inhomogeneous detunings that are difficult to compensate for. So the nice thing is that this also gives us a sense of sort of the region of forgiveness where we're able to operate our tweezer wavelength. So maybe something like 0.05 nanometers around the magic wavelength is still okay to get a high loading probability, which really accounts for both the loading efficiency and also the imaging efficiency. And this region of forgiveness is expected to become more forgiving, if you like, as you go to lower and lower trap depths. So the next question for us naturally is to figure out what is the minimum loading trap depths and also the minimum imaging trap depths that are required. So for this, we basically vary the trap depth during the loading stage. And we also re-optimize at every single trap depth the parameters, the loading frequencies and intensities, and we measure what is our best loading probabilities. And we find that it saturates at about 80% from 0.7 millikelvin onwards. And before we wanted to do a comparison on the increase of scalability of tweezer arrays on our part, we wanted to check whether we really needed to go to AC tweezers for the D2 light, or if we could actually still load with D2 lambda gray molasses in DC. And we thought, oh, maybe we could be optimistic because after all, in free space, we could achieve 50 microkelvin. Although bearing in mind that the scalable polarizability told us that the D2 state was, the P3 half state was a little bit anti-trapping.
5 minutes.
For us, we found that actually we were not able to load in D2 DC at all, consistent with what the NEET group had found. In fact, we can't load for more than 10%. And we were wondering why this does not work. And we thought that it's probably because of the breakdown of hyperfine states in the presence of the tweezer trap due to the tensor polarizability components. So the P3 half has tensor polarizability components. And in order to perform lambda gray molasses cooling, we had to be blue detuned relative to the F equals to 2 transition, and still red detuned relative to the F equals to 3. But this spacing is really only 58 megahertz for sodium in free space. So there wasn't very much room for us to play with. So this forces us to use AC tweezers when we want to use D2 light. So now we come to sort of the punchline slide of this talk, where we try to figure out what is actually the minimum imaging trap depth required using this DC-D1 approach so far. And we find that with DC-D1 imaging, and we always use DC-D1 gray molasses loading in this case, we're able to saturate the loading probability at 80% from trap depths as shallow as 0.5 millikelvin onwards. And this is in contrast to the AC D2 imaging, where the AC is now required, and that saturates only at about 5 millikelvin or so. So there's really a factor of 10 in terms of the power that is required to produce the kind of trap depth. So I know that actually for the AC case, we are actually reporting the peak imaging depth. And again, this is just to reflect and emphasize the fact that to create this much trap depth, you really require 10 times as much power. So this order of magnitude reduction in the tweezer power per trap gives us a corresponding increase in scalability. And we also want to emphasize again that these DC-D1 methods are really applicable to all the alkali atoms. Okay, and then so far all that work was done for a single tweezer. We also show that actually for a 1D array of 8 tweezers, we can increase the loading we maintain the loading probability to be relatively high. It's probably a little bit lower just because of some small inhomogeneities in our trap depth. And we find that the loading detuning is actually quite sensitive to the exact trap depth. Okay, so very briefly, what's next? Well, we want to go from 8 to more traps. So here's actually a picture of, for instance, 41 by 41 traps, although there are no atoms yet loaded in these tweezers. And also, of course, we want to induce interactions. There are 2 ways to do that. First, by either exciting it to Rydberg state, or actually by forming ground state ultra-cold dipolar molecules. And there it has been demonstrated that you can have long coherence times, but you do have extra degrees of freedom to control, namely the vibrational and rotational degrees of freedom. One way to do to induce these dipolar interactions using molecules is to assemble them using tweezers. So this was really pioneered in the Ni group, where they just showed actually the ground state sodium cesium molecule formation. And this was done by actually trapping individual sodium and cesium atoms, cooling them to the in tweezers, cooling them to the motional ground state, merging them together to form weakly bound molecules, and then finally transferring them to the ground state using this 2-photon stirrup transition that you see over here. In this case, this is really a potential that you see for sodium potassium. This method of molecule assembly was successfully done in the bulk for several different molecules, first KRB in 2008, and then followed by a string of other molecules. And so the idea is to really do this on a single molecule level with the tweezers. And in fact, with these molecules, you can control interactions either by applying a DC electric field, where in this case, you can change the range of the interactions and also the anisotropy of the interactions. And we also showed recently in the Zuerlein group that where I had done my postdoc, that you can actually control these interactions using microwaves by dressing basically on the J equals to 0, rotational state equals to 0, and rotational state equals to 1. Excited state, and there by dressing the molecules and by shining in another probe microwave field, we can actually see this outlet town splitting, where basically the outlet town splitting gives us a sense of the Rabi frequency. And yep, so with this, I think I'll summarize. In summary, we have shown that the D1 magic wavelengths are very useful. We want to thank the Clark group for calculating and predicting these numbers more than a decade ago. And they've really given us a very useful increase in the number of tweezers that we can now create with a wide variety of species really going forward. And this will actually be very nice for sort of assessing different species for richer interactions, be it through controlling different Feshbach resonances or just by forming dipolar molecules. And I'd like to thank the members of my group. The work that you heard about was really led by graduate student Mujahid, and also with contributions from Lu Heng, Xiu Quan, and also Krishna over here. This picture that you see is taken before the COVID pandemic, so nobody's wearing any masks, but ever since then, we've had several wonderful group members who joined us, and we're always looking for more people to join us. We have open postdoc positions with a flexible start date, and also we're starting to look for PhD students from next August onwards. So thank you very much for your attention.
Oh, thank you very much, Huanqian. I mean, I'm very happy to see all the progress that you made since you started the operation. Really nice. Okay. So do we have questions?
Yes, I have a question. Thank you for this talk. So I have a very basic question. I'm not very familiar with tweezer. Then you will excuse. So. I understand that actually there is a certain control of interaction between the atoms, right? So does this magic wavelengths are useful in this direction? So in particular, is it possible, say, to control the interaction as Oliver Morsch was saying, using facilitation, basically dipole blockade? And so is it possible to see this interaction migrating along the tweezers?
Yeah, so thank you for the question. I would say that in terms of this D1 magic wavelength, it is more for just the scalability, just in terms of larger qubit numbers, if you like. The interactions would be a separate issue. And especially if we were to do it with Rydberg atoms, the Rydberg atoms cannot be trapped with these tweezer light, in fact. So during the Rydberg experiments, if we were to use just a simple Gaussian beam, we would have to turn off the laser during the Rydberg experiments. So the interactions are kind of like the next step. It's a different ball game. Yeah.
Okay. Thank you.
Thanks.
Gerhard? Yes, I was sure.
Thank you very much for the promotion. Is this the next step, or the following the next step you want to do, that you want to do the interactions with Rydberg states, or you want to use the dipolar interaction you were promoting in your talk?
Yeah, so we're actually exploring both avenues at the moment. We do also have potassium in our chamber. Mm-hmm. So I think there are many exciting directions to be pursued in both stages, really. So yeah.
And if I use a follow-up, so you showed us the nice image of about the 41 times 41, well, let's say foci, is that there are no atoms in there. So do you have enough laser power to get the half millikelvin or whatever D1 trap depth you need to load this with atoms?
Yeah, so that's an excellent question. So we don't have all the way for 41 by 41. That we would probably, okay, so if we were purely limited by tweezer laser power, we would probably be able to generate something like about 100 of those. And I say this because basically 8 traps, each trap requires about, say, 2.5 milliwatts. And right now we're actually using a 1 watt laser. And so then you might ask, well, since you have a 1 watt laser, why don't you show me more atoms arrays compared to the 8 traps? And the reason is because actually our microscope objective right now has pretty bad coma aberration, unfortunately. So we're limited a little bit by that coma aberration. But yeah, with an upgrade, we would like to go for more traps. Yes.
Okay, thanks.
So let me have a very simple question. So you showed, I mean, the beautiful structure made by the people in Paris, right? Okay, so the Eiffel Tower. So when do we get the Merlion?
Yeah, so for that we would need to include a spatial light modulator and also some electrically tunable lenses. But yeah, that would be quite a dream, right? Actually, there's a question in the chat. So it says, what is the required background pressure of the target atoms to get the loading that you showed today? So thanks for the question. The background pressure is lower than 10 to the minus 10 millibar. And actually we get that pressure just by operating our 3D mod, loading the 3D mod actually from a 2D mod. So the 3D mod, where the tweezers are, is not exactly where the dispensers also are. So we can actually get away with fairly low background pressures. But if I'm not wrong, actually, a lot of these tweezer array setups also do work with background pressures roughly in that range. It doesn't have to be very low because we are actually looking at fairly fast cycle times over here. Thank you.
I mean, let's thank again, I mean, Huanqian.